Hello there, my name is Chris Power and I am a professor at Western University in London, Ontario, Canada, and I'm presenting my work on electrical resistivity tomography for monitoring the remediation of DNAPL source zones and how we assess this using numerical, laboratory and field experiments. Before I begin, I'd like to acknowledge my two key collaborators, Jason Gerhard and Panos Surlos. So NAPLs, or non-aqueous phase liquids, remain a major environmental, economical and technological challenge. They are highly toxic, slightly soluble and pose unacceptable risk to human health and the environment. So NAPLs can either be LNAPLs, which are lighter than water, such as gasoline, and DNAPLs, which are denser than water, such as chlorinated solvents. In North America alone, we still have hundreds of thousands of sites that have been contaminated by various NAPLs, and this has resulted in the spending of millions and millions of dollars every year to both manage and rehabilitate these sites. So following release at the surface, a NAPL, which in this case we're looking at a DNAPL, will migrate vertically downwards, penetrate the water table and then redistribute in response to the local lithological variations. And we end up with a complex and heterogeneous distribution of DNAPL, which comprises both free product and residual DNAPL. And it's this particular distribution, which we call the DNAPL source zone, that we are striving to accurately characterize and then monitor during remedial activities. And this leads to the motivation of geophysical techniques, which can provide cost-effective, non-invasive, rapid, and continuous information in both space and time. So my contribution to this research area is to evaluate and try and advance ERT in time-lapse mode for monitoring DNAPL remediation and looking at this at the field scale. So we looked at this via numerical, laboratory and field studies, which I'll go through quickly one by one. So first of all, numerical. So with the numerical study, we first developed a new and valuable couple model, which linked a DNAPL multiphase flow model to a ERT model. So again, taking the key hydrogeological parameters from the multiphase flow model and converting those using petrophysics to the corresponding electrical properties, in this case bulk electrical resistivity. So following the development of this model, we had a highly valuable and cost-effective exploratory tool that could be used to comprehensively assess the performance of ERT for monitoring various DNAPL spill scenarios. So looking here at the multiphase flow model, we've released tetrachloroethylene over 5 days, and then turning off the source, you can see the tetrachloroethylene redistributing in the subsurface over 6 months. And this is typically our scenario prior to remediation. You can see here 0% remediation. So this is really the scenario that we typically, when we typically arrive on site, this is the scenario with an existing DNAPL source zone in the subsurface, and then when we implement our remediation strategy, we will slowly, or sorry, not slowly, but we will dissolve or remove or destruct our DNAPL mass over time. So again, just to highlight that with this particular model, we have a lot of flexibility and we can simulate a wide range of different DNAPL scenarios with different DNAPL types and different soil matrices and different soil types. So for the purpose of this presentation, I'm just going to quickly summarize one of the spills here, which is a chlorobenzene or CB DNAPL here. So this is our time 0 scenario prior to the start of remediation. You can see the 0% DNAPL mass reduction here. And then after implementing remediation, we've just removed 20% of that total DNAPL volume. And we can isolate and highlight that exact DNAPL reduction. This is the actual reduction that has occurred. And we can do that over time with different volume intervals. In this case, I'm picking 20% volume intervals. You can see the blue is 40%, the yellow is 60%, the green is 80%, and the magenta is 100%. So again, we can nicely highlight using this ISO volume here or this cross section here of exactly where the DNAPL has been removed. And moving that now to the left hand side, which is the actual DNAPL remediated versus what surface ERT has measured over time. You can compare actual to ERT measured, and again comparing the evolution of the DNAPL source zone over time as it's being remediated. This powerful combination of knowing exactly where the DNAPL has been remediated and then knowing how ERT would have performed, you can really extensively assess the performance of ERT and how it will have been used to monitor the DNAPL program. So again, we use this for a number of different spill scenarios. We've published some work on this already, and it still sits there as a very powerful tool for a range of different scenarios, whether it's looking at advancements in geophysics or advancements in DNAPL remediation strategies. It's a very powerful and cost-effective tool for that. Okay, so experimental. As is well known, surface ERT tends to lose resolution or resolving ability with depth, and we typically would turn to crosshole or borehole to borehole ERT. But when it comes to a DNAPL source zone, or a DNAPL being the target, we are unable to install vertical boreholes directly through a DNAPL source zone. So that's one constraint. And the other constraint being that we are constrained by the spacing between each vertical borehole. So again, while it's traditionally an alternative to surface ERT, crosshole ERT also has its limitations, particularly for a DNAPL site. So this led to the motivation of a surface to horizontal borehole ERT configuration, where we place electrodes in a horizontal borehole beneath the DNAPL source zone and use a combination of surface and horizontal borehole ERT to optimize and increase that resolving ability of the DNAPL. So horizontal electrodes from a geophysical perspective have already been studied in tunnel to tunnel, and also direct push implant electrodes. And more importantly, from a DNAPL perspective, horizontal remediation wells continue to be increasingly used at DNAPL sites because they provide a greater zone of influence and contact length between the remediation injection or amendment fluids and the DNAPL source zone. And this is exactly what we always like to achieve with ERT, is to get the ERT electrodes as close as possible to the target, in this case the DNAPL source zone. So again, these nicely go hand in hand. We performed a number of numerical simulations, and also carried out a tank experiments as well for this work, just to assess the feasibility of this approach. So here we have a 1 meter cube experimental tank, and on the right hand side we have the a 3D visualization of the setup here, where we have a medium sand staircase surrounded by a fine sand material. So when we inject the NAPL through into the medium sand, it will only prefer to migrate within that staircase. As you can see here, following 200 milliliters of NAPL injected up to 400, the NAPL will prefer to stay and migrate through the medium sand, and as it's unable to overcome the displacement pressure of the surrounding fine sand. So that gave us greater control of where the DNAPL will move during the experiment. So looking at the comparison between how surface ERT would have performed and how surface to horizontal borehole ERT would have performed, you can see here, after 200 milliliters of NAPL injected, the surface ERT, because it's been injected in the bottom, is unable to resolve that, whereas surface to horizontal borehole ERT is well able to resolve that initial injection. And as we increase up to 600 milliliters of NAPL, again, because it's so deep, surface to horizontal borehole ERT is performing very well, whereas surface ERT is struggling. And it's only when the NAPL gets closer to the surface that surface ERT is able to resolve that shallower NAPL region. So again, clearly highlights the benefit of using surface to horizontal borehole ERT. And finishing up with the field study that we've done, which was at a field site in New Jersey, USA, undergoing remediation. It was a 37-acre farmer manufacturing facility that produced 20,000 tons of coal tar, and the lagoons that it had been placed in unfortunately leaked, and this resulted in the contamination of 200,000 cubic meters of soil. So this is just looking at a site map here and looking at lagoons C and D, which were the biggest problem on this site. This is a test pit that has clearly has standing NAPL phase here. And then we have a deeper soil core, again clearly contaminated by DNAPL. And then this is just a sample of the DNAPL extracted from the subsurface. Following these site characterization activities, this is a conceptual model here. Over here is lagoon C and D, and you can see the extent of that DNAPL spill or release from the lagoons. So at this site, a thermal remediation technology was used, which in this case is a smoldering remediation technology called STAR. It works by heating up the contaminated zone here up to a maximum or up to as high as 1000 degrees Celsius temperature, which smolders and burns off the DNAPL source zone. So you can see here that over time this treated region gets bigger, and we end up with this complex region of heated water and vapors, increased water temperatures, and also this dry zone behind the smoldering front. So from a geophysical perspective, we have a temperature increase. So the water temperature is increasing, which we know will actually decrease the resistivity. This is followed by, as this increase continues to occur, the water will boil and burn off. So then we have, a significant decrease in water saturation. This leads to a significant increase in resistivity. And then after some time, the groundwater will flow back into that dry zone. So it causes a subsequent decrease of resistivity again. So the considerations here is we have three different phenomenon happening at once, and they're all conflicting each other, so it's something to appreciate the complexity of this problem. And also at this site we had buried metal objects for the injection well and also the thermocouples. So again, it's a challenging task for both data collection and also the following interpretation. Okay, so field installation, two ERT lines were set up over over a zone undergoing thermal remediation. These are the electrodes being installed. This is the thermal remediation facility, and these are the ERT lines set up using the Cisco Pro. In total, 2 lines were used with 36 electrodes at 60 centimeter spacings. Okay, so this is the ERT images at each line prior to remediation. You can see here. And this is remediation monitoring. So these are going to be time-lapse images taken during the remediation. First of all, let's look at the bottom here. These are the temperatures that were measured by the thermocouples on the site. You can see here we have low temperatures that massively increase here during the thermal remediation and then slowly decrease again. Similar to the CO2, this is an indication that the remediation, the process is working when we generate these carbon dioxide gases here. So again, we can see the increase in carbon dioxide during remediation. And then we have electrical resistivity here from the ERT lines as well. So looking up here at the time-lapse ratio image, we have red, which is a positive change, white will be a 0 change, and blue will be a negative change. So looking here at where the resistivity is, if you look here, the resistivity hasn't really changed yet after the initial start of the remediation. But then we have a reduction here, and that corresponds to the little increase in water temperature we have here. So that's that first decrease in resistivity. And then as the temperature significantly rises here, we end up with that burning off of the water, and that's that corresponding significant increase of resistivity. And then as the process starts to slow down, the temperature, the water cools off, and then that groundwater flows back in, resulting in this slow decrease in resistivity back to initial values again. So just to highlight this with this focus analysis, we're just going to look at a few key nodes here. You can see again, this is just again a summary of what's occurring from a temperature perspective. We have this little increase in temperature, and then we have this massive spike which burns off the water, and then that cools down again. So if we look at a few individual nodes in the ERT time lapse, we have that initial decrease in resistivity, then we have that high increase in resistivity when the water is burned off, and then that's followed by a decrease again. And this is just looking at a bunch of nodes to confirm this process where we have a decrease, increase, and then decrease again in resistivity. So just to finish up, looking at the current work, some couple modeling where again we're taking the DNAPL multi-phase flow model and now connecting that to time domain and frequency domain IP models. We're doing some DNAPL and SIP experiments, and also we're about to perform a pilot test at a field site with surface to horizontal borehole ERT. So conclusions is you've seen a framework for a systematic and controlled approach for evaluating ERT for mapping DNAPLs. I've shown you a new exploratory tool for assessing time-lapse ERT of DNAPLs at the field scale. You've seen the proposal of a new surface to horizontal borehole ERT configuration to enhance ERT performance, and also the application of time-lapse ERT for monitoring DNAPL mass reduction at a field site. Before I finish, I'd just like to acknowledge some key people, especially Lais Trento, who performed the field work in New Jersey in partnership with Savron and Geosyntec Consultants, and also Angelos Albanis, who's now working on the DNAPL and IP work. So I'd like to thank you all for listening. I'm happy to take questions via email at cpower24@uwo.ca. Thank you.